We have now discussed how we can solve for the time needed for the temperature of a lump system to change by a certain amount. Now we will discuss the criterion for us to consider an object to be a lump system. The parameter that we use to determine whether an object can be considered a lump system is called the Biot number. It is also sometimes referred to as the dimensionless heat transfer coefficient. The physical significance of the Biot number is that it allows us to compare how resistant the object is from heat conduction versus how resistant its surface is from heat convection. What we want a lump system to have is for it to offer very little resistance to heat conduction. This will allow heat to diffuse easily through the object, which will then cause the temperature gradient within the object to be as low as possible. This is the formula for computing the Biot number. The ratio of the characteristic length of the geometry to the thermal conductivity of the object is divided by the reciprocal of the convection heat transfer coefficient at the surface of the object. The general formula for the characteristic length of an object corresponds to the ratio of the total volume of the object and the total cross-sectional area from or to which convection occurs. Once we have found the value of L sub c, we can now substitute it to the formula for the Biot number. A lump system is an object in which the corresponding Biot number is less than or equal to 0.1. As a final note, the formula for computing for L sub c is applicable for whether the object is a plane wall, a cylinder, or a sphere. We can simplify the general formula for computing the characteristic length during cases of one-dimensional heat conduction in which both surfaces of an object is exposed to the same condition. For one-dimensional heat conduction, in which both sides of the wall experience the same convection heat transfer conditions, the characteristic length for plane walls with a thickness denoted by twice of L is half of this thickness. On the other hand, for cylinders with a radius of r sub O, the characteristic length is half the radius. While for spheres with a radius of r sub O, the characteristic length is 1/3 of this radius. Now, once we have computed for the Biot number, we can consider the object as a lump system if the computed Biot number is still less than or equal to 0.1. Finally, before we leave the topic of Biot number, let us investigate further what its physical significance is. By manipulating the formula for the Biot number, we can write it in this form instead. Now, if we multiply a change in temperature, T, to both the numerator and the denominator, we will see that the numerator assumes the formula for the convection heat flux, while the denominator assumes the formula for the conduction heat flux. Therefore, another way by which we can express the physical significance of the Biot number is that it relates the rate of convection heat transfer at the surface of the object to the rate of heat conduction within the object.